Okay, good evening, everyone. I'm Mike Walter, and I'm director of the Geophysical Laboratory. And on behalf of everyone here on this Broad Branch Road campus, everyone at the Department of Terrestrial Magnetism and the Geophysical Lab, I'd like to welcome you tonight to this very special neighborhood lecture series talk. It's my great pleasure tonight to introduce our speaker, Dr. Eric Isaacs. Eric is currently the 11th president of the Carnegie Institution of Washington. He began that role in July of this year, so not quite a year at the helm. Eric has a very long history, and he's trained as a materials physicist. He got his PhD at MIT in 1988, working on magnetic semiconductors. Don't know if we'll hear about magnetic semiconductors tonight, but perhaps, who knows. After that, Eric went to the Bell Labs, where he worked for 15 years as a postdoc and as a staff member eventually, directing both the materials physics departments for some time and the semiconductor physics department at the Bell Labs. In 2003, Eric went to the Argonne National Labs in Chicago and was there for, I think, about 13 years in a number of different roles. From 2003 to 2008 as the director for the Center for Nanoscale Materials. Spent a time for a year or two as the deputy director of the scientific programs at the Argonne Labs. And then from 2009 to 2014 was the director of Argonne National Labs. At the same time, Eric was a professor of physics at the James Franck Institute at the University of Chicago, and eventually from 2014 to 2016 was the provost at the University of Chicago. So that's a long list of scientific leadership, and that leadership continues now at the Carnegie Institution of Washington. And today, Eric is going to give us a presentation on addressing climate change with science-based energy solutions. So thank you very much, Eric.
Thank you. Thanks, Mike. First, let me say welcome to everybody, as Mike has. I'm new to Washington. I've just moved here about 7 months ago. Actually, just moved into an apartment downtown about 4 weeks ago. And it's really great to see the energy, the excitement, and all of you coming here from the neighborhood and appreciating the kind of things that we do here at Carnegie Institution for Science. I also want to welcome Maxine Singer, who's here. She's one of my predecessors. I'm the 11th, you said? She was the 8th. That makes you the 8th president of Carnegie, so welcome, Maxine. So I'm going to talk about energy. It's one of the most important topics in my mind. I'll try to sneak in some materials physics because I'm a materials physicist, but mostly just give a big high-level picture about some of the challenges, but also some of the exciting things that are going on around the world, but also here at Carnegie, trying to address this inextricable link between energy, climate, water. These are some of the big problems we're facing. And the big question, of course, is this one. How will our future energy demands be met? And what I really like about this photo, I've loved this for a long time, but it's a satellite image, obviously taken over a period of time. You don't get nighttime on the Earth all at once. But it shows you two things. First of all, the incredible waste of electricity. All that light should just be in, shouldn't be coming out. But that's one thing. But the other is you look at how dark a lot of the continents are. And that darkness is becoming lighter as time goes on. That drive for economic development, that drive for economies all over the world is driven only because there's more energy to use. And so it's really one of the most fundamental problems of our time. And this sort of shows you that at a high level. One of my, he was a colleague of mine, but the quote here is really to describe the magnitude of the problem. Richard Smalley, some of you know, he was a Nobel Prize winner in chemistry, and he died about 10 years ago. But even just before he died, he started thinking a lot about energy. I was on a panel with him. And he coined this idea of the 50 terawatt problem. What does that mean? Today we use about 17 or 18 terawatts. That's a lot of energy. Just compare that to a light bulb at 60. This is a lot of energy. And many people now project, of course it's hard to predict 80 years, 90 years into the future, that by 2100 we'd be using 50 terawatts. And as you'll see, the consumption of energy is directly related to the amount of carbon we're producing. And so if you triple the amount of energy we use, it has a very direct impact on the environment, very direct impact on how we can afford to live on the surface of the Earth. So this really states the problem at a really high level, but it's a really well-stated problem. This is a busy figure, but it says it all too. This basically overall shows you, and I should say what this is plotting. On the vertical axis, it's basically energy, and it's given in a funny unit in tons of oil equivalent, right? So tons of oil equivalent. We all, as Americans, use about, so a ton of oil equivalent is about 7.5 barrels of oil. Each of us uses some number, maybe 10 barrels of oil a year. So when you talk about tons of oil equivalent, it's a big number. And one ton, as I said, is about 7 barrels. So if you look at that, a typical American, you go back to the United States. I should say one other thing. The colors represent just regions. So the green is Asia and the red is the Americas. On the horizontal is basically the gross domestic product per capita. So what this is roughly telling you, although it's scattered, is there's roughly a linear relationship between the economic power of a country, the GDP of a country, and the amount of oil they use. And that's a very important statement. So as we develop, some of these countries are going to become bigger and bigger consumers of energy. It's just an inextricable link. It just happens. And the other thing to notice is that China and India, which are by far the biggest countries on the planet, are still we're talking about fairly low consumption per capita of electricity or of energy in general. So as these countries develop, and they are developing very rapidly, there's going to be, and that's what's driving that 50 terawatt problem, they're going to be consuming more and more energy. So that's an inevitability, I would say. The other thing I would say here is that this is per capita. China and India are very populated. So if you actually look at the total use of energy, China's already ahead of the US. China's already using more energy and producing more carbon than the US is. And that's not going to stop because there's still 1.2 billion people. They're 3 or 4 times bigger than we are. And so that's going to continue to go down, continue to grow and grow and grow. So the main message from this is that that economic development directly related to energy, and that the countries that are in the phase of development have yet to be fully developed are going to consume more and more energy as time goes on. So I just actually found this today when I was tooling around looking for something about global warming. And this was recently produced last year by NASA. Actually, maybe it was just released this year by NASA. And what it's an attempt to do is take the whole globe and show you the temperature as a function of time. It turns out that essentially since the Industrial Revolution, and for better or for worse, for better for scientists, it turns out that since the beginning of the Industrial Revolution, there's enough data on Earth to start actually making maps about what happens. So just watch this movie and you can see what happens. So what this is it's a measure of temperature. You can see in the upper left-hand corner what the colors mean. Dark blue is -2 degrees. Red is +2 degrees relative to the average over the whole Earth. And you can see what's happening here over time. And these are 5-year averages. So each change in the movie is a 5-year frame. And what you can see happens over time, especially when you get into the 60s, 70s, and 80s, is you get more and more of the red. And the red keeps getting darker and darker. And now we're just approaching current day. As you can see what's happening. It's hard to miss what's happening. So what's actually happened here is the average temperature on Earth has gone up by about 1.4 degrees Fahrenheit. That's mapped over the whole Earth. It's gone up about 1.4 degrees since 1880. And what you also see is the distribution of that heating is not uniform, for better or for worse. So you see where the heating is mostly prevalent is over where there's a lot of ice. That's not a good thing. So what you're seeing here is that there's an average increase. We're not talking about 20 degrees increase, we're talking about 1.4 degrees Fahrenheit, less than a degree centigrade. Why should we care about that? So what? If you go back in time and look at what started the Ice Age, that was only a change in 1 or 2 degrees total in the surface temperature of the Earth. So a 1 degree change is very dramatic, and we're starting to see the effects of that. And I'll talk a little bit about those effects, but what I really want to focus on is the future of potential mitigation strategies, not just what the problems are, but also what potential solutions are. So I want to start, though, with just the US, because that's something that we have lots of really good data on. Just to give you a sense of what of what consumption looks like in the U.S. What's the distribution of energy? How do we use energy in the U.S.? How do we use it for various means, but also what's the source of energy? And so what you see on the top row here in these different colors are the different energy sources. The different colors are different energy sources. And again, I'm sorry, there's a lot of different units. If you try to ever look up energy online, you'll, as I am, totally confused by every single, there's kilowatts, there's quads. We use 100 quads in this country. It goes back to about it's about 3.5 terawatts. So we use about a quarter of the Earth's energy here in this country. That's important, but not terribly important for the point of this discussion. But think of the total here being about 100. So 100% is 100 quads. And so about 36% is petroleum. That's the petroleum we use. About 5% is biomass. That's burning wood. That's burning things like that. Coal actually has gone down recently, but it's still 15% or so. Natural gas, as you've probably heard, has increased in its usage, which is probably better than petroleum and coal, but it's still a fossil fuel. And if you look carefully where it's very interesting to think about technologically, if you look at the truly carbon-free sources, we know the ones on the left are all fossil fuels and create lots of carbon. The ones on the right, like geothermal, wind, hydro, solar, are as you know, carbon-free, but they're a very small percentage of what we actually have. So if you look at the total, you're seeing only a few percent in wind. So when you hear in the community that we're going to go all solar and wind, that's a great idea. But the reality is we're a long way from doing that. That fossil fuels are here to stay in many ways, but the percentages, as I said, are small. They're growing, but they're small. What I also like to show you is, I'll go through this. This is a great diagram, but it's very complicated. But I do want to show you that there are two primary uses of energy in our country are, number one, for transportation, which is over here on the left. So if you follow this spaghetti diagram, which I won't ask you to do in detail, most of transportation today is through petroleum. So I'll talk a little about electrification and what that could actually mean for us in terms of reduction of carbon. And the other application is electricity. That's about 40% of the total use of energy in the US, right? So 40% is electricity, about 28% is transportation. Taken together, that's 2/3 of our energy consumption. And that's a very important number to remember. The other thing to look at this diagram, which is a bit of a heartbreak in some ways, is look at the amount that's wasted. So if you look at the total, about 42% is used, but the rest of it, 57, 58%, is just wasted. So that's why you hear a lot about how do we recover the waste heat, the waste energy that's not used. And so this is an interesting diagram because it shows you, number one, we still have most of our energy consumed from fossil fuels, and it's not going to change overnight. And it's not going to change, as you'll see, fast enough. So we have a real problem. The other thing to see is, of course, the way it's distributed. Transportation and electricity are two of the most important things. If you're going to reduce your carbon footprint, reduce your consumption of fossil fuel, those are two very important things. But there is the possibility of a strategy, and I'll talk about some of it. Petroleum people are now talking about fuel switching. They're talking about going from very carbon-heavy fuels to less carbon-heavy fuels and renewables like biomass. And we can talk about that. I won't talk much about it because it's an interesting thing, but it's a long way away from having any impact. Talk about electric energy storage, which I will talk about. Energy storage can displace a lot of the carbon produced in transportation and the grid. So also thinking about a more efficient grid. You can think about carbon capture. So I already said that we're going to continue to use carbon. We're not getting out of carbon so quickly. If you could do carbon capture, which is also, we have a lot of geophysicists in this particular part of our institution here, and they will tell you it's almost unimaginable to think about taking the 30 gigatons of carbon we produce and sticking it in the earth, although you may tell me different, right? Right, Mike? Yeah, right. So that, carbon capture, you hear it all the time. It's a great idea, but we're really far technologically from being able to imagine doing it. And the real challenge there is even if you could do it today, you would have to make sure it's stored there for many millions of years, because the day that gets released is the day that everything goes to hell. That's another example. The other is, and I'll talk about zero carbon energy. We'll talk a bit about that. Solar, wind, those are great things, but I've already told you that it's still a small percentage. But there's hope. Smart grid and transmission, end-use efficiency is very important. I'll mention this a little bit, and then climate science, which is extremely important because we want to understand the impacts of all this energy use and carbon production. Anyway, I could spend a lot more time here, but the main takeaway here is that most of our energy is still produced by fossil fuels all over the world, not just here, that the percentage of alternative energies is small. But that's not to say there's no hope. And so this figure really shows you the kinds of, if you really think about a sustainable energy economy, these are the kinds of things that we're thinking about. And I've already kind of mentioned this, right? You're talking about wind. I'll talk a little bit more about wind. Wind is very hopeful. Combined with solar energy, there's a lot of hope there, but there are real challenges to it, which I'll talk about. Electrical transmission, smart grids, thinking about how to take the variable sources that are wind and solar and transmit it on a transmission grid. At 2%, it's pretty easy. At 20% penetration of solar and wind, I'll show you why it's really hard. That's why you need energy storage. You need ways of what's called load balancing. I'll talk about that. I've already mentioned sequestration. It's absolutely essential that this country pursues this. We have some research going on, not nearly enough, but we have some research going on in sequestration. But again, that's not going to be the only solution because it's just a massive, massive thing. I won't talk much about it anymore, but nuclear energy is really interesting. Maybe after the talk we can talk about it because that's something which we haven't built a reactor in this country in many years, since 3 Mile Island, but the rest of the world is. China, Russia, they're building nuclear plants almost daily right now, and it is an interesting path forward. In fact, one could think of nuclear as a stopgap for the next 50 years while we figure out how to scale solar and wind and other forms of alternative energy. So let me just talk about a few the bright spots. This is just interesting stuff that's going on in the world now with energy. We all know about turbines. There's not any new science in this, but there's a tremendous amount of interesting engineering. And this I just pulled out the other day because I found it very interesting. Right now, we have quite a lot of wind energy in this country. It's still small, as I've said, but we have quite a lot of wind energy. But the world's largest wind turbine today is about about 7 megawatts. The reactor I showed you on the last page was about it would be 1,000 megawatts, so it's a gigawatt. So it's 1,000 times, or maybe 500 times more energy than one of these things. But today we get a capacity that's about 7 megawatts out of a wind turbine. But it's really all engineering. But I thought this was cool because these are getting better all the time, right? In fact, this particular turbine, which is now being advertised by GE, it hasn't been built yet. They're building it. This is 12 megawatts. I'll come back and maybe we'll understand a little bit more about scale. But 12 megawatts is many hundreds of homes. It would power many hundreds of homes at once. And right now they're building a couple of these in Denmark. They're going to start building these windmills. And what the impressive part about these windmills is really the technology that goes into building these things. You can just see on this lower right-hand corner the scale of this thing. This is the Eiffel Tower, and this is the Chrysler Building. So we're now talking about wind turbines that are essentially as big as those buildings. These things are remarkably large. And this one in particular, as I said, is about 12 megawatts. So that's really exciting. That's going to come around this summer. Worldwide, there's about 600 gigawatts in wind right now. 600 gigawatts. I know I'm throwing energy out at you quite a bit. Remember that the U.S. alone uses about 3 terawatts. So that's about 5, 6, 7 times the total amount of solar in the whole world. And we don't own most of the solar. I mean, the solar is everywhere around the world. So these numbers are big, but not nearly big enough. Another example is this one. This is a really cool, brand new solar array in India. It's 2,500 acres. It's about 650, 700 megawatts. Again, that's about the size of a big nuclear power plant or a couple of big coal plants. What's interesting about this is that it was actually deployed at about $650 million for 600 megawatts. 650 megawatts is enough for hundreds of thousands of homes. So this is really powering quite a lot of Indian homes in the province in which it exists in. If you wanted to power this whole country, take the U.S., just to give you a sense of scale, what it would take to do solar for the U.S., it would take something that's a lot bigger than this. It would take something, hope no one here is from Kansas, but if you took Kansas and dedicated the whole thing in Kansas to a solar array, you'd have enough energy basically to power our whole country. That's several terawatts of power. That's a lot bigger than this one. But nonetheless, it's happening, and it's happening fairly rapidly. But here's the rub with solar and wind, which you probably know about, which is they're not there all the time, right? And so far it hasn't been such a big deal for us, and here's why. because, so this is these are examples from two different kinds of, this is a wind farm in Minnesota, this is solar radiation. You all know, right? So the bottom, this kind of green curve here, sitting down here, these are days on the bottom, and gigawatts, that's billion watts on the top. And it's a big wind farm. It's a 1.5 gigawatt wind farm, so it's one of the larger ones in the Midwest. And you can see, not surprisingly, some days, like the 10th day here was very windy. The 9th and 10th day had plenty of wind. It was blowing all day, and you had the wind farm running all the time. I don't know how many of you have driven from LA to Palm Springs, but if you go by there, you see one of the largest wind farms in the country. But if you go by there, most of the time, more than half of the turbines are not running. The reason is because it's actually more expensive to run them than not, because maintenance is expensive on these things, and it's very expensive actually to get up very high and replace the various mechanisms, so they turn them off. This is just the wind blowing and not blowing, but there's many reasons why wind turbines are on or off. What that means, though, is of course that when it's off and you happen to need the energy, what do? This is a little bit more complicated up here. The yellow line is the actual load. It's the consumption in Minnesota of the actual energy, and the blue line is the load minus the wind. So somehow the power company in Minnesota has to supply the yellow line, and when you have wind, you've got an additional variation on top of already a variable that's the load. And you ultimately, of course, you don't want to leave people without power. The load varies on a daily basis, of course, because when people go to sleep, they turn their air conditioners off, et cetera. So load varies, and the message to get out of this is that you have this variability with wind. Same thing with sun, and these are 3 days, 3 different days in 2009. It doesn't matter what year you're in. You see the red line, which is a really good day. It was a perfectly clear, sunny Midwestern day. Whereas you look at the green line, it was a very cloudy day, and they almost got no sun out of it. And that's very important, again, for the same reason it's important here. Now, the main point on this slide is that today, we're less than 10% total on these types of sources, so we can absorb that kind of variability, can be absorbed in the current network. But when you get to 20% or 30%, forget 50 or 60%, which is where we'd love to be. I mean, that Kansas solar array, we'd have real trouble because you have this issue of on-off, and obviously you've got to meet the needs of people when they are in the hospital or what have you. So this variability turns out to be fine for 10% or less when your penetration is low, but as soon as you get to 20 or 30%, the energy companies can't handle it anymore. So that's a really important thing to remember. So what's the answer? It's energy storage. And energy storage is, you've probably heard this yourselves, that unless we solve the energy storage problem, you're not going to solve the problem of being able to introduce wind and sun into a community. I have a good friend who runs the largest privately held wind and solar company in Chicago called Invenergy, and he's told me for many years that if somebody doesn't invent the batteries we need, we're not going to be able to do. Ultimately, he's not going to be able to make money, but we're not going to be able to do what we have to do. I mean, an energy company wants to be able to, what they call load balance, so that when you're demanding energy, they can supply it to you. They also want to buy low, sell high, so they'd like to store the energy that they're producing all the time and sell it back to you when they can charge you an extra dime for a kilowatt hour. But what the good news here is that this is an example. This is actually in Southern California. This is one of the largest battery farms, if you will, in the country. It's just under about 100 megawatts, so that's a lot of storage capacity. But it's not nearly enough, but it is something. These are starts, and I'm going to talk a little about batteries now, but these particular batteries are lithium-ion batteries. You've heard of lithium-ion batteries. It's a technology that's kind of there, at least on this kind of level. You can kind of do it. Right now, I think worldwide we have, in terms of storage, mostly in batteries I'm talking about, we have about 160 gigawatts. Again, that's just a number, that's a big number, 160 billion watts of storage capacity. Various organizations like the International Energy Agency and others estimate that if we're going to start reducing our carbon actually to zero additional carbon starting by 2030, we need to at least double that in the coming, now it's only down to about 12 or 15 years, and it's a question whether we'll be able to do that. But it's with big banks of batteries that it'll happen, so that's very good news. So, we're making some inroads. Now, the other thing I mentioned early on with that spaghetti diagram was there's the grid, which we have to learn how to control, and we want to introduce these variable sources. But there's also the automobile, right, which is a big deal. Transportation is a big consumer of gas, as you know, and it's a big producer of carbon. This is back when I was at Argonne, but now this is sort of well known, that it turns out it's a Gedanken experiment. If you could take the U.S. transportation system, take all light trucks and all of your cars, all of our cars, and you can electrify them, the U.S. transport system would do the following. Basically, you'd be able to reduce consumption by up to about 7 million barrels a day. So just to give you a sense of how big that is, that's a lot. We import about 10 million barrels of oil a day, and we export something smaller than that, but we're using about 20 million. So that's about a third, roughly a third of the oil consumption if you could electrify all cars. And that's a big challenge, but by the way, China is looking at that. By doing that, you would also reduce the well-to-wheels carbon footprint by 25%. So you're reducing the amount of carbon produced by cars by 25%. So it's a huge win if you can do it, but the scale of the challenge is immense. And so I show you here a Tesla 3. It's a very nice car. A Tesla 3 was the world's best-selling EV last year. They sold about 140,000 units. A Tesla 3 is basically, as I kind of joke, they're getting better and better, but it's basically a battery with a car around it, because you basically have several thousand AA batteries. It used to be they used laptop batteries, which are very flat thin. Now they use what are almost like AA. They're all lithium batteries. And they're actually pretty good. You can buy a car now that's got a 200-mile range. You can even spend more and I think get one that's got like 300-mile range. Some of you may even have one. I've noticed there are a lot here. Although we have a branch in San Francisco of Carnegie, and it's like if you don't have a Tesla, you're not allowed to even pull onto the highways. I don't know if you've seen it. Just to give you also a sense is that, in this country there are hundreds of millions of cars. I think there's roughly at least a car per person, including children. But worldwide there's about 1.2 billion cars. So the opportunity here is huge if it's doable. I'll come back later with a caveat. And the reason that this is actually happening, and we're going to get a little into material science now, the reason that we're able to do this is that even just a few years ago, go back to 2012, a battery in a car, and I'm just going to do a little math here, a battery in a car cost about, to make these car batteries, these 7,000 laptop batteries or whatever Tesla's using, cost about $800 per kilowatt hour. So just as a number, if you want to drive a car, a Tesla, say, 200 miles, you need about 50 kilowatts. That's 200 miles in a Tesla today. That's the one you go buy, you pay whatever, you pay your $2,000 deposit, and you get your car, and you pay the whole. So that would be, so if you want a car that's $800 per kilowatt hour, and you wanted 50 kilowatts to drive 200 miles, that's going to cost, the battery itself was $40,000. That just gives you a sense of cost, and that's a big deal. That's important, right? I mean, we're driven by that, no pun intended. Today, very quickly, amazingly rapidly, so we created a battery hub at Argonne, which intention was to reduce the cost by 5, and we're almost there already. So, and this is not Argonne, this is an international play. Here in 2018, we're talking about being already, the Tesla is already about $200 per kilowatt hour. So it's only now $10,000 for a 50 kilowatt battery that drives you 200 miles. That's everything. So you've just shaved $30,000, and that's why the Tesla 3 can happen, because that's already happening. So the economics of it are exciting, and that's great. And as you may have heard, this is Tesla's battery plant. I don't know if you've heard about this, but they built this in Nevada. I think it's only half done, but this is the so-called Elon Musk's Gigafactory, and the idea here is to produce 50 gigawatt hours or 50 gigawatts by 2020. So that's only another year from now. And remember, 50 gigawatts now, that's 500,000 cars. If we're talking about 100 kilowatt batteries, that's 400 mile. That's like a tank of gas. So he's actually going to start producing, or they're going to start producing, the ability to make 500,000 car batteries a year. So this is actually happening. It's exciting. Still well short of the many millions of cars we have, and well short of really displacing petroleum, but it's really starting to happen. So what I thought I would do is explain to you, because you're probably thinking, well, it's only a battery. Explain to you a little bit. I couldn't resist, because I'm a materials physicist, is talk a little bit about battery. So I'm going to tell you a little bit how a battery works. And you'll understand why it's so complicated. It's a really complicated object. You have to basically combine engineering, physics, material science, chemistry to really understand how to make a battery work. And so I'm going to play a battery for you. I'm going to show you how it works. So what you're seeing now are lithium ions. This is a traditional lithium ion battery. They're sitting over here in graphite. So what graphite is to a battery is when a battery is charged, you take lithium ions. These are atoms of lithium that are charged. They have a one positive charge. And you put them on a bunch of shells. Graphite is literally a bunch of shells. Graphite's a very interesting, unique material. A lot of people here work in carbon, but it's a different structure of carbon called diamond. This is a different structure called graphite. It's a magical material for batteries because basically it's easy to put the lithium on the shelf and pull it off the shelf. You put it on, you pull it off. And when you charge it, which is what's happening now, you're putting lithium on the shelves. And then, so it's plugged into the wall, it's charging. And now you plug it into your car, or you start your car, and it starts coming back the other way. So lithium now is discharging, coming back to its host material. So the way you deliver lithium to the battery is in a complicated material, usually made up of 3 or 4 different elements. Lithium, cobalt, oxygen, lithium, iron, phosphorus, oxygen, very complicated materials. And I don't want to bug you too much with it. But the point is that this is a source material in its natural state. You put the lithium back in. When you're charging, you bring it back to these shelves and store it there. And that's how a battery works. There's a lot of complication in this because, first of all, this is a material that likes to be what it is. When you pull the lithium out, it no longer has the same state. You know, materials physicist friends here will understand it's a totally different material without lithium in it, and it crumbles, it falls apart. It's no longer what you started with. So you're actually taking an intrinsic material and pulling it apart and asking it to hold its shape, hold its form. That's not easy. What also happens is all this gunk here, and I'll call it gunk, although if you're a battery expert, this is a solid electrolyte interface, which forms as you cycle this thing, because you've got these charged particles moving back and forth, moving through this liquid, which is called an electrolyte, which support the charge, and you create all this stuff at the interfaces of these electrodes, and that's another problem. It's sometimes good because it protects the electrodes, but then it also piles up and becomes like crust, and it's hard to penetrate. So all these things together make a battery quite difficult. Not to mention safety issues. These things can flare up sometimes. You've heard of that. They can all these different modes, and you can get chemistry you don't want to get. You can get all kinds of things happening. So it's not such an easy science. Even with that, that's how a battery works. It's called a rocking chair, basically. This is how a battery works. But there are a lot of things you can do to improve a battery because, for example, when you put lithium on a shelf, it's not really strongly held there, and it turns out it's fairly weak energetically. You can actually put it on something else so that it's more energetically favorable. And what I'll show you now is that I won't show you the details. There's many other possibilities to replace this lithium battery with much higher energy densities. And so, the point is, and I should say why you want this, right? Right now, as I kind of joked, a Tesla is a battery with a car around it. You really would like to have an object that's no heavier, no bigger, no denser than a tank of gas, right? Ultimately, you want a car to be comfortable. I mean, I'm not saying the Tesla isn't a great car. It sounds, I've driven them, they're great. But there's a lot more you could do if you could do more energy density. And so there are a lot of different technologies. One example is silicon. So you take silicon, everyone knows silicon, it's what's used in transistors. It turns out it's also magical with lithium. If you replace the graphite with silicon, you can actually stuff 25 times more lithium in that than you can in graphite. The problem is that silicon doesn't like to have all that lithium in it. It cracks, it breaks apart, so it's material science. Magnesium is another option. Instead of lithium, which we all know, you take magnesium. 2 reasons magnesium is great. Is much more plentiful on Earth, magnesium. It's the 6th most plentiful element on Earth compared to lithium, which isn't as much. But the other reason is magnesium, instead of having a single charge, has 2 charges. So for free almost, you double the capacity of that battery. So that's a little material science. That's really how these batteries work. But they're very appealing. There's a whole lot of different ideas. But the bottom line is batteries are really developing very rapidly. There's a long way to go technologically from a material science point of view, from a chemist and an engineering point of view. But there are really interesting things being developed, and these will happen. It's just a matter of time and money. But now there's one thing I want to back out a little bit and say, which is that it sounds great, electric vehicles, and free, it's basically burning nothing. But you got to remember, how do you get the energy for an electric vehicle? You have to plug it in. And it turns out where you plug it in makes a big difference. And so this is one of my favorite figures. It was developed by this guy, Michael Wang at Argonne. It's called GREET, which is basically to not just look at what the battery can do and drive the car, because certainly an actual car that has a battery has no emission, right? You'll never see a tailpipe on a Tesla. But you still plug it in, and you plug it into a grid. And that grid may very well have a lot of coal on it, or that grid may have other kinds of natural gas on it. Today, it's more natural gas. So what we've done here is studied what's called well to wheels. So, what does it actually take comparing, say, gasoline? Gasoline's amazing stuff, by the way. Gasoline has energy density, which is hard to beat anywhere. The battery I just showed you is about 20 times less energy dense, meaning that's why there's such a big amount of batteries, and they're heavy, and that's why it's big. Gasoline is amazing stuff given to us by geophysicists, I should say, organic material and geophysicists, or geology anyway, over the years. It's amazing stuff. But it also has, of course, the carbon problem. So just want to tell you a little about this because I find this figure, it's very busy but fascinating. What I'm plotting here are different types of grid mixes, or different kinds well, the first one is actually just a car with gasoline, different kind of gasolines or natural gas, right? These are and diesel, right? And what it shows you is per kilometer how much carbon is produced, okay? So if I take the standard, today's vehicle, it's somewhere between 450 and 400 now. It produces about half a kilogram of carbon for every mile you drive. So just remember that when you go out to the supermarket or when you go home tonight, you're producing a half a kilogram of carbon, which is a lot of carbon. And so cars are pretty notorious when it comes to producing carbon. If you look at the gasoline car, that's what it produces, about 400 grams or a half a kilo of carbon per kilometer. These all are different types of grids, right? So all this stuff down here are electric vehicles of different kinds. There's a plug-in hybrid. But let me just look at let's just look at a battery electric. So let's assume we have a 150-mile range car. This is a couple years old. It could say 250 today, but it's 150. And you have a battery car like the Tesla, and you plug it into a grid. Let's just take the U.S. grid. On average, if you plug it into a U.S. grid, remember you're getting electricity out of the grid now, and you know what the grid mix is. On average, if you look at well, this may not be true anymore with the current administration, but with the Obama administration, they had targets for basically the grid mix, how much carbon generating energy, coal versus gas, natural gas versus nuclear, et cetera. And if you look at what the 2035 grid looks like, it's about almost half of what you see in a gasoline car. So that's actually a good thing, right? You would say in a more modern grid, that's 2030, 2035, you're going to have a grid which has less carbon on it, so when you plug it in, you're going to produce less carbon. And this is, of course, you've got to be careful who you say, but if West Virginia is a very coal-intensive state. It looks a lot like China looks like. Turns out if you plug the same car into a grid in West Virginia at the 2010 mix, which hasn't changed a lot, you're not doing any better than in a gasoline, an internal combustion engine. So why do it? If you use the California grid, even from a few years ago, the California grid actually, it turns out, is much better than an internal combustion engine. So that's why there's so many Teslas. It actually makes sense in California to plug your car into that grid. So my point here is that you really have to, when you're thinking about electric vehicles being a panacea, you also have to look at the whole system. You can't just look at the one thing. The other thing I'll say, not to diss my friends in China, China's pushing a huge policy on electrification for cars. China is not the place you want to plug in because China is actually about 80% coal, 70 to 80% coal now, and they continue to build coal plants. So it's a great thing that China is trying to lead on electric vehicles. From an economic point of view, it'll be great for China. But it is not the answer to reduce carbon. And you'll see in a few minutes, actually, they haven't been very successful in that. So that's really the moral of this story is just because it's electric doesn't mean it's good. Now, that's what you're climbing up one level from, I've just described to you a couple of technologies. Obviously, solar and wind are really good. They're totally carbon-free. They're not high penetration yet. Automobiles and going electric, very good, but still have to be careful about the grid. But you really have to think about multiple integrated technologies. And I want to spend just a few minutes on some work by one of our scientists, Ken Caldera, out in our global ecology department, about a project he has called Net Zero. And really the point of this, there's 2 points to this, right? This is now not just an automobile and plugging it in. It's not just wind. It's not just solar. It's thinking about the whole system. So one of the things he does is model the whole system. And he wants to get to a net zero grid, right? So you want to have a net zero grid. But part of the issue is that this figure, and I won't go into a lot of detail, really, this was recently published in Science, really highlights the challenges that we have. And the challenges are on both sides of the equation, on the side of the production equation and on the side of the requirements. And the whole point of this slide is that, first of all, a couple points to it. One is, certain things like hospitals demand very high reliability. And I just told you that the issue of solar and wind presents some problems. So as soon as you think about that and you start thinking of increasing your carbon free, you really have to think carefully of what it means to have a hospital on one hand, which requires very steady source. And by the way, nuclear is about as steady a source as you can get. It's flat all the time and always and needs to be. That's one of its strengths, but also weaknesses. So the idea that you have these types of things on the grid, wind, I mentioned, and solar are variable. They produce a carbon-free source, but they're variable. So when you start thinking about all these things together, I mentioned, if you have 20% wind penetration, you really have to think about modeling the whole system. You can't just think about, it's great to have wind, it's great to have solar. But one of the most important pieces here is that even if I take all of this together and I go green, all these things on the right-hand side or lower right are green, there are certain elements of this which are very hard to decarbonize. And that's where we're going to have our biggest challenges. And so I just wanted to talk briefly about what's hard to decarbonize and why it's hard to decarbonize. So, electricity we've talked about, and it turns out, in principle, you can start thinking about decarbonizing. And if you can go solar, if you can go wind, and you can go nuclear, you can decarbonize electricity. But there are certain things that'll be very hard to do. One is load following electricity. When I showed you this variability in, not just in the wind, but you look at the availability, even the variability in use diurnally, from day to day, you have to have a source that follows. So for example, if you have a nuclear reactor, it doesn't want to be turned on and off every night, right? You have to store the energy somewhere, or you have to find a way to dump the energy somewhere else, or you throw it away. Right now, we throw some energy away as a result. So their load following electricity becomes very important when you add more and more variable things onto the grid. So batteries are one way to handle that. Peaker plants you've heard of, natural gas is another way to handle that. These are plants that are easy to turn on and off. Coal plants, nuclear plants are very hard to turn on and off. It takes hours and hours to fire them up and turn them off, so you don't have them. So load following electricity turns out to be a very hard thing to displace petroleum, coal, or nuclear, and you're not going to do it. Aviation, shipping, big thing, airplanes. So when was the last time you flew an airplane? That's growing rapidly. It's very hard to do that without real fuel, without petroleum, because of the energy density, right? So if I told you, let's replace it with a battery, there's two problems with the battery. I can't deliver the power fast enough, because that is an issue. That's a safety issue. But the other, frankly, well, we won't go there. We don't talk more about it. We're already laughing. Nobody wants to fly that. Yeah. I mean, maybe a coal-powered airplane, but certainly not one that's aviation, shipping. The other thing that we don't think a lot about, but when we look at the skies in India, we look at the skies in China, a lot of that pollution, it's particulate, but also carbon, is due to the fact there's a lot of construction going on. And I don't know if, I'm certainly old enough, I was young, but I went to Europe. You go to Europe in the 50s and 60s when they were rebuilding after the war, there was a lot of that too. A lot of it was rebuilding Europe, and so we're seeing the same thing in Asia now. Cement and iron are very carbon intensive, not only soot, not only particulate, but they're very intensive. So these wedges are going to be very hard to displace. And just to give you a sense of how much they add up to in terms of carbon, let me back up a little bit. We produce on Earth what's about 3 billion tons of carbon a year. So we're producing 33 billion. That's a number down here. So the amount of carbon we're producing through all these different means, cars, jets, electricity production, all over, is about 33 gigatons. We're putting up into the atmosphere, we're putting 34 gigatons in the atmosphere. Just for a reference, naturally, if we did nothing, if we were back 1,000 years and there was only wood fires, which is a tiny fraction, and the populations were low, did nothing, there's about 700 gigatons of carbon naturally metabolizing through the atmosphere, into the oceans, back into the soil, et cetera. The fuel, that's the carbon cycle. Many people here know that and study it. But the point is, so we're putting up 5% every year into the atmosphere of carbon. That's a big deal. These hard to destroy or hard to get rid of, difficult to eliminate emissions amount to 30% of what we do. So we're still talking about a large number of carbon producers that are going to be very hard to eliminate. I'm not saying this to you to make you upset, but I'm saying it to you to realize that, when you hear, this Green New Deal is fantastic, it's going in the right direction, but it's impossible to wipe out all carbon. It's just not going to happen, not in the near future anyway. And of course, now a little bit back, more of the bad news, all of you have seen this, right? The fact that with all the things we're doing, we're still seeing warming, we're still seeing carbon, so we're not really stopping anything yet, right? We're seeing all these things, so the big news that just came out, it was just a couple days ago, I think, is that we're still, our carbon emissions are still going up. And in fact, the carbon emissions have gone up another 2.5% in 2018, exactly concomitant with the amount of energy consumption increase. So it's about 2.5% on each. So we're seeing, again, driven by energy. The things to worry about are all the collateral damage. Climate change, certainly the climate change and the issues of insurance. You've probably heard these stories, right? So this is Munich Re, which is one of the largest reinsurance companies in the world. They do insurance for coastal towns, coastal houses. They're already warning. It's to their benefit to warn we're going to raise our rates, but they're raising their rates largely because of actuarial numbers. So you see all this stuff going on, and it's pretty scary. So this is, you've seen this too. This is, of course, the fires in California, which have been pretty severe. I want to emphasize that it's not hopeless. A lot of science can get done. A lot of things can be done. I mean, a lot of the technologies I've showed you already are important. But there's a lot of canaries in the coal mine, and this sort of gives you a sense of what's changing. These are some examples from Carnegie. Some of our Carnegie scientists recently, coral bleaching, there's something like 110 coral reefs around the world. Of those, about 90 are already bleached or on their way to being bleached. This is a healthy coral, and this is a bleached coral, and so we're trying to understand what the mechanisms are. When you warm the water, we know you're warming the water. We know you're acidifying the water by salinity. What's actually happening? It's science. Scientists actually, some are even giddy because it's changing the world and it's something to observe, but it's a really bad thing that we're seeing. You've heard also about things like algal blooms, which are coming around because water temperatures are warming just a little bit, but enough that it's now a better host for algae. A lot of this is not driven just by temperature change, but by nitrogen runoff. So the food for these things is nitrogen. They're metabolizing nitrogen. So a lot's happening that's complicated and interrelated. I want to finish. A couple more minutes? How much time do I have? I just want to finish so I told you a little bit about technology and a little bit about the changing Earth, but the big question is science and technology is great, and the stuff that's happening will keep happening, and we should be very excited by it. This country certainly should be investing more in it. We're not investing enough. China and India is. They're not always the best players, but they're certainly investing in the science. But the real issue is, can you not just do the science, but also think about the right national policies? So I just wanted to give you a little bad news and a little good news on policy at the very end. And it's a basic fact that you can regulate, right? So one of the things, we talk, for example, about switching for automobiles from gas to electric. It's not just going to happen it's not going to happen fast enough purely economically. Same thing on the grid. You're not going to see that change. I mean, we're talking about many, many years before solar and wind are entirely the same cost as just digging up coal and petroleum. Petroleum now is actually fairly cheap. So the real question is, what can policy do? And so this is an example actually from one of our other scientists in California, Anna Mikulak, and she was able to get data from a Japanese satellite called GOSAT. It's the Greenhouse Gases Observing Satellite. It's actually the first one that's dedicated to looking at greenhouse gases, the two main ones, carbon and methane. And so since about 2010, China has had a pretty distinct and clear policy about coal mines. Coal mines, I mentioned before, I think coal is 70-75% of their power, their grid. And so they're also digging a lot of coal. They're buying a lot of coal from Australia, but also digging a lot of coal in China. Coal releases methane. Methane is, on the short term, a very bad greenhouse gas. And what this figure shows you, due to results from the past several years, what you're looking at, this bar down here is parts per billion, which is just the increase in, relative to some 2010 number, an increase in the amount of methane. What you're seeing in China in particular, but also a bit in India, and Africa, for similar but different reasons, you're seeing a continued increase in the methane production from those countries. The policy said you produce methane from digging coal, you've got to capture it. And what's interesting here is that there are actually inspectors for each of those sites, but what we believe is happening is the inspections aren't being done truthfully, and that you're seeing that there's a good policy in place, but the policy is not getting followed. And that brings me to my final example, where we do see a positive effect. And we see the effect in India. India is actually terribly polluted, as you know, but they actually have some interesting policies they're trying to implement. This is the state of Gujarat, which is the most industry-intensive state in India. It's not far outside of Delhi. I think it's west of Delhi. And the picture you're looking at is Ahmedabad, which is the largest city in Gujarat. It's not so bad, right? But a couple of years ago, a colleague of mine, an economist, did a study there and then a policy change. So India, like China, has policy on particulates and on pollution, right? And so what they did is went into Gujarat. There's some 20,000 factories there, 20,000 factories, and they did a sampling of about 1,000 factories. So I want you to just look at this plot. It's a lot of data, but I want to go through it a little bit so that you can understand it. So this plot here These are just a list of different companies. Each bar represents some set of companies. And the vertical is essentially the particulate count, right? And this upper plot here I should say the red line represents the regulatory limit on how much particulates can be produced in any given factory. And what you're seeing, the red line is about 150 particles per, I think it's ppm, parts per million, of certain size particles, of certain distribution of particles. And what you look at, if you were to go to Gujarat and just look at the records, you'd say, well, great, no one's polluting. If I showed you a picture of some of these states, you would know everyone's polluting. But magically, everyone falls just below the line. So it turns out, I won't get to the reason yet, but I'll tell you what's going on here, is that the inspectors that do the work, that inspect and report, are being paid by the companies themselves. So the auditors aren't independent. They're being rewarded, basically, to do this, right? So this guy being an economist, his name is Michael Greenstone, being an economist, said, wait a second, that's not good incentive, right? So instead of listening to this result, they went out and did their own study, and they found this result, right? Of course, you see the huge distribution. So certainly some, maybe almost half the factories were actually obeying the regulation, but the other half were not obeying the regulation. So instead of following this, they just revamped the whole process and just basically said, okay, we're going to do a few things. One is companies can't pay their auditors. We're going to have a pool of auditors that are picked by the government. The auditors won't get paid by the individuals. The companies will pay into a pool, and then from that they'll get. And then when they go back and do the reinspection, the back check, if it turns out that they were right, they get a bonus. Very simple. This is an economist now, right? It turns out they were able to do a tremendous amount of change, and the change is remarkable. I mean, these are standard deviations, which are meaningful, but not, right? The actual quantitative change in industrial pollution, these are particulates, was almost a third. So the reason I'm telling you this is that technology is great. If we can get the technology working, it's going to be important, but it is so important to get the policies right and to get some of the processes right to make it all work. And so what India has done most recently, probably not only because of this study, but largely because if you just go to any Indian city today, if you go to Mumbai, you go to Delhi, you go to any of them, you'll see why it's very important. It's cars, it's construction, it's pollution. The new ministry of India, the Ministry of, I forget which ministry, I'm sorry, is targeting a 25% reduction in particulates. And if they do this kind of thing, it'll work. And India is a very important target for this, right? There are actually studies which say that life expectancy is directly tied to the amount of pollution, and so there's a real argument here for why this has to be done. So I think I should finish up here. You know, the cost, a lot of the things I'm describing for you, the technologies, whether it's solar, whether it's wind, nuclear I didn't even talk about. That's a whole other topic, which I decided not to, this is too much, but you know, we really have to worry about cost for sure. That's important, because everything I'm suggesting, like with cars, is that it's cost-driven. I get that. But we also have to think carefully about economic investment, because it will be an investment now for a future that's changed. And the cost, we clearly know the cost of global warming. I mean, it's just, we're over the edge now, and the question is how fast can we reverse that? So I will stop there and be happy to take any questions. Do we have a microphone? You want to hand a microphone out? Okay.
Thank you. Questions?
I could use my Marine Corps voice, but I won't.
That's okay too.
So yeah, this is all really great, and just to say, I work at Joint Base Andrews, and we're looking at building energy resilience.
Yeah.
So we looked at placing a natural gas plant on the base to basically circle the wagons. But we realized that Aberdeen Proving Grounds actually installed 6 or 9 hydrogen fuel cells to power the critical infrastructure. So we're going to go up and inspect and take a look and see what they did and see if it's going to be something that we'd like to do. So, and plus the hydrogen highway that's still being built in California. What does hydrogen look, because I know that wasn't done any of the things, and I know it's small and it's expensive and the standards aren't there, but can you give us an indication?
Actually, it's very appealing, actually, and it's something, I just didn't have time to talk about everything. So, but you know, the idea behind hydrogen is, as you burn hydrogen and you just make water. So it's a great idea, and it ultimately, if you can do it, and it's an onboard source, so you just basically fill her up with something like water or something like hydrogen. The challenge with hydrogen has always been splitting the water in the first place, getting the hydrogen in the first place, and then compressing it so that you have enough density and hydrogen can be explosive, although that's maybe less of a worry. Actually, BMW built a car. I don't know if I drove a hydrogen car. Yeah, they're really great, and they're quiet and they're clean, just like a battery car. So it's all good, and it's on the list of things. It was actually in the diagram I showed you, which was the net zero. Hydrogen is a key component of it. It's just, again, releasing that hydrogen and then filling stations. So today, the way the U.S. is configured and the way most countries are configured, it's still much easier to plug into a grid at night than it is to produce hydrogen. But I actually think hydrogen is a great solution. What I'd suggest to you instead of fuel cells is why don't you guys just build a small modular reactor? Because on a military base, it's safe, you're protected, right? You worry about security, you worry about and you produce 100 megawatts of power, which is perfectly clean. And so I know there are people trying to promote this on military bases because you have the defense, you have the protection. I actually think that would be very interesting because, well, to restart nuclear in this country is going to take something like 10 nuclear or 20 nuclear small reactors to be built first to make it cost affordable. So that's what you should do. Who am I to tell the Department of Defense what to do?
Can you say anything about why the water wave technology is just going so slowly? I mean, the density is out there, the quantity, the charges that are available from gravity from the moon far exceed our consumption. It's just nobody knows how to tap it.
Well, I think people are learning. Again, that's part of the mix of things that people are learning to do. I know the Taiwanese, because they have these incredible currents off the east coast of Taiwan, are thinking about these big turbines. They've got a few that are already in. The big challenge with turbines is almost trivial, but it's salt water. So they're looking at how you put these things down. I mean, the turbines we're putting in the air, right? This 12 megawatt thing that I showed you is probably similar to what you get in a turbine in the water, but at least it's in the air. The biggest risk there is the birds, and that is actually a big deal. But those turbines are just more naturally easier to make. The difficulty, I think, of plant. Now, I'm not an expert in tidal energy. Where they do use it is the easy place, which is the Bay of Fundy, which has got this amazing tide, and they're using that. But to actually use what you're saying, which are the currents, is a really interesting idea. And its day may come. It's just, and it is part of the mix. I don't have enough of an opinion to know other than there are some challenges with it.
Thank you, Doctor. Is this on?
Okay.
You mentioned, I have a specific and a general. With regard to the specific, you mentioned that today's power companies cannot absorb more than 20% of wind and solar. And I didn't understand why that is, so if you could give some further explanation. And the second thing is, with regard to nuclear, would you offer an opinion as to whether there is a scientific consensus that we ought to be building more nuclear power plants?
We have a lot of scientists here. Ask if any scientists ever consent on anything. But let's put the scientific consensus aside for the time being. Let me answer your first question first. The higher penetration of solar and wind is a challenge because everything for a power company is what's called load balancing, right? They basically have to supply on-demand power. So when you turn your light switch on, you get light, right? And more extreme, of course. When people drive at home at night, you get home at 6 o'clock. You saw those I don't know if you saw that, but if you looked at even in Minnesota, a modest-sized town, there are diurnal variations, right? When people go to sleep, the power consumption goes down, and when they get up, they start using power again, whether it's washing machines, dishwashers, air conditioning, or heating, or what have you. And so to accommodate, so that's they know how to do that. But when you add on top of that variability in the source, so right now, historically, right, they had coal, they had some nuclear. 20% of electricity in this country is nuclear, coal, nuclear, gas, natural gas now, so-called peaker plants. The coal and nuclear were very flat, so they still had to deal with this variation, but they did it with things called peaker plants and in other ways. Sometimes, in fact, you probably heard this, they'll dump energy. If you have too much energy, you just dump it, which for them is just a waste of dollars. So the issue is you're adding more variables onto the grid, which makes it more complicated. And those variables aren't simple to understand. You can't plan for them in advance. They happen. So how do you make sure you have the capacity to fill in the troughs when the wind dies down? So if you're depending on like that Indian thing, if you're depending on 600 megawatts of power, that's like a nuclear power plant, 600 megawatts of power, and the wind goes away. That's 600 megawatts that's all of a sudden not there. How do you deal with that? And that's why you need what's called load leveling. So load leveling means that when it's windy, I can store the energy. I give to my customers what they need, and then when the wind dies, and I siphon some off, whatever I can, to put into a storage, whatever the storage is. And then when the wind dies, I still have capacity to give them. So at a few percent, they can do that, and it's not costly. When you get to 20%, all of a sudden, it's much more difficult to provide that much power, right? That 20% could be many tens of megawatts or even hundreds of megawatts in a city. And how do you do that? So that's why it gets more difficult. So if we dream of going to 50% solar and wind, which is, by the way, if you just look at the insolation, look at the amount of sun on Earth, you can do that, right? We've got this great fusion reactor in the sky. You can use it, but it's these complications which absolutely require storage to resolve. And like the other thing that's used is these natural gas turns out to be great because you can, like your stove, you can just flame it. You can just turn it on, it heats up pretty quickly. So it turns out natural gas is a little like, it is the answer to some of these problems. But if you're really talking about eliminating fossil fuel, natural gas is sort of a stopgap for that. So that's the first question. Is there a consensus by scientists? Well, no. I mean, nuclear is a very complicated topic, right? I mean, it's complicated. I don't have to explain why it's complicated, right? I mean, there's issues of radiation, but the radiation issues are minimal, but I don't think everyone understands that. And so there is a move afoot now to think about, there are low levels of radiation. Last time you flew from here to California, you got a pretty high dose, more than you get ever if you live near a reactor. But that aside, there are these issues that the perception and real issues about nuclear. Scientists will generally say, yeah, of course, you want to do it. Even, by the way, I think this Green New Deal even says, let's do nuclear, right? So this is really the left of the Democratic Party saying, let's do it. So the scientists as a whole are just like people and have the same concerns about nuclear as everybody else. But I think in particular with the modern designs, and there are new designs. We haven't built a reactor in this country since 3 Mile Island. There's 2 under construction that were off and now they're back on again, that's right. And these are the big ones. These are the gigawatt scale. These are tens of billions of dollars to build these things. So there are a couple coming in now. Those designs today are much more modern and they don't rely on active coolants. Their safety features are much better. Does that mean there's a zero risk? Of course not. But the safety features are passive. They rely on gravity to cool. They rely on many things which are, from a technical point of view, an engineer's point of view, much better solutions. We're holding back the U.S. We're building these 2 right now. China and Russia are building them all the time, right? They're building them constantly. Korea has about 24 reactors. They want to build a fast reactor. They want to build what's called a breeder reactor. So the rest of the world's going ahead, whether or not we want to. We've lost some of the engineers, a lot of the engineers, or even the training. We don't have many programs that train people to be nuclear engineers. So we're at risk of never being able to repeat that, and we'll have to buy it from the Chinese, which I don't know if we will or we won't. But I think when you ask if there's a scientific consensus, I think scientists, like anyone, have their concerns because there are risks, but the risks are, in my opinion, as a one scientist, pretty low compared to the displacement of carbon and the things you're seeing and going on around the world. Okay, we'll come back to you.
I read a little bit about an idea that seems a little scary, global warming, putting sulfate aerosols into the stratosphere to reflect off sunlight so we won't have problems with increased heat on Earth.
Yeah. This is called geoengineering. Again, my friends who are geologists and environmental scientists. So there is this notion that basically you can change what's called the albedo of the Earth. So we're getting global warming because we have these light-trapping gases in the atmosphere, methane and carbon. I mean, there are a lot of light-trapping gases, but those 2 in particular are the ones we're producing. And so there's this notion that if you can create a reflecting surface over the Earth, that you can reflect more light back into space, right, and send it back out. And it turns out that, just to give you an idea of the numbers, if you can increase the reflectivity of the Earth by 1%, that's worth about 1 degree. So that's almost what we already have, right? So if you could take 1% of the Earth and reflect all the sunlight with a big mirror, in principle, you could cool it off. Now, that's a very simplistic view because Temperature changes are global, and reflection could be very local. There's a study, an engineering study out there where you take these big ships, you go out into the middle of the ocean. There's certain places in the ocean where the currents, the airflow is calm enough that you just basically boil a bunch of water, and you end up with these clouds. You create clouds. I mean, you could seed them. You're basically going to seed them and boil. And so there is a notion that you could change the reflectivity of the Earth. It's an untested idea. A lot of people believe, including some of my colleagues here at Carnegie, believe it's a total waste of time because, first of all, because global warming is such a complicated, it's not just the reflection of the Earth, there's a lot of other things going on. But there are ideas out there that you could change the reflectivity of the Earth and reduce the temperature, or at least salvage what we have. It's an interesting one, and I think it should be studied, but I can't tell you that it could work.
I wonder if scientists have looked down the road, so to speak, about all the lithium batteries when they reach the end of their lifespan. What's going to happen to them?
Yeah, that's a great question. Recycling? It is true that if you just look at the amount of lithium that we now have that's already been mined, there's not nearly enough to meet even what they want to do at Tesla. There's not enough. So you'd have to go back to mining again. There's a lot of lithium in the Earth, but we just don't have it on the surface of the Earth. So for two reasons, recycling is going to become very important. Lithium isn't intrinsically a very bad thing. It's a little bit, it can explode, but not the same way other things can explode. So you can keep it dry. As long as you keep it dry, it's fine. But it is a really good question, and it's one in which, like lead acid batteries, right, which, the lead, which has been, historically, of course, we haven't worried much about lead. Probably some of you, I know I don't, but some of you throw your batteries out still, right? And those batteries are some not such good chemicals. So for two reasons, reprocessing is going to become very important. There actually are even some companies already out there. One just failed, unfortunately, where you weren't going to buy a battery, you'd rent a battery, so they would. It was called Better Place. It was in Israel. And they were funded out of a company, and they were funded out of a venture capital company in Silicon Valley. And basically, they did this in Israel. I actually drove one. It's very cool. They had a bunch of stations. You'd drive in. They would drop the battery out of the bottom and put in a new one, which was already charged. So you wouldn't even have to worry about this idea. They'd be recycling them anyway. But it is a really important question. And in fact, the batteries have better lifetimes than ever. But they're, I don't know how long you keep a car for, but I like to keep a car for 10 years, 12 years. And the battery lifetime may not be that long. So it's a great question. Lithium is different than the kind you typically have in your, it's like the one in your phone. It's rechargeable, which is a lithium battery. All batteries are not rechargeable, which are worse because you can't keep using them. But recycling is going to be the only way. And that comes back to this holistic idea. You've got to think of this not just isolated as batteries.
Yes, please. I had two questions. One about nuclear energy. There are two ways, to fusion and fission.
Right.
So we always have been told that fusion will be the future.
Yeah.
But when I was studying, they say
it's
for a
Right.
few years, then few decades. Then what is the point? If you can say something about it.
Yeah, I can say a little
And the second question is about the way to, you say it's very important to store energy. And are there investigation, research on the change of phase? I don't know if this is the right word. When you change a liquid to a stream or a liquid to a solid, are there research on this?
Phase change.
Yeah,
always.
phase change.
There is,
Thank you
but
very
I think that's more of a futuristic thing. And since we have a lot of questions, I'll answer the first one, and then maybe we can have a conversation afterwards about phase change stuff. Fusion versus fission. So fission is here. Fission actually still needs development. I think we know most of the technology, and the ideal technology for fission, and I'm going to scare everybody here, is actually fast reactors, right? Which were the original reactors designed by Enrico Fermi were fast reactors because they burn up. It's called fuel cycling. You actually recycle your fuel, getting back to the lithium problem. You recycle it, right? You create pretty reactive materials, but it turns out you can breed future materials. So essentially, these breeder reactors are actually breeding the next fuel for the next reactor. So fission in itself has several types of reactors, which are still not fully deployed. Korea's doing a lot of work on fast reactors. We used to, we don't anymore, and others do as well. Fusion, it may always be of the future. There's a big project now in France, in southern France, called ITER, which is an international, what's called a tokamak, but it's an international project where they're dumping a ton of money. This is a multi-billion-dollar money, international. We're involved in it. It's had its fits and starts, but they're actually going for at least a break even. They're going to go see if they can confine a plasma. You have to, so the idea there is you're doing fusion, so you've got to have something that's compact enough, right, and hot enough so that you go from, let's call it 4 hydrogen atoms to 1 helium atom, and then you suck out the energy that's released in that collision, in that fusion. It's very hard because it gets very hot, and so far we've not even come close to being able to extract as much energy from the thing as we actually put into it. It's actually great physics, plasma physics. So there's a big project going on. There's a few smaller projects here. There are actually companies in this country that are working on trying to develop fusion. And there's one company that thinks they have an answer. They confine the plasma with magnetic fields. They heat it up. They haven't got to sun-like temperature. You know, you have to get to pretty hot temperatures. You have to get to the heat of a sun. You're creating a sun inside. So it's a really hard problem. But I actually, you know, that's another example of something which may still be 50 years off, but is totally worth exploring. And we're not spending that much on it anyway. I think it's a great project. So we can hope. Back there, and we'll come forward then.
So I've heard that one of the main problems with nuclear energy and nuclear power is that we haven't figured out a solution to disposing of all the nuclear waste yet, and I was just curious as to what your opinion was on that.
Well, we actually have. I mean, frankly, Yucca Mountain was a fine solution, which Harry Reid decided to kill. It really was a pretty good solution. But I agree. I mean, you still have nuclear waste, and you have to deal with it. You have to ship it across states, and right now we don't have a solution because Yucca Mountain was closed. Obama closed it, which I thought was actually not a good move. Much as I liked his energy policy, which was all of the above, nuclear wasn't one of the all of the above. So that's one problem. It is a problem. Right now, all reactors that are operating, and most of the ones that were originally built are still operating, those reactors are storing the fuels locally until they can figure out what to do. We can get into a long discussion about that, but we're still waiting. That is something that has to be solved. The fast reactors, still fission, fast reactors are actually much better because they burn up most of the fuel. A current reactor burns 5% of the fuel, and the rest of it you put in a holding tank. A breeder reactor burns 95% of the fuel, and only 5% is left. And the 5% that's left is highly radioactive, but has a short lifetime. What you really worry about is not highly radioactive. You're worried about something with a 100,000-year lifetime. That's what you're worried about, because then it's going to sit there forever emitting radiation. So Yucca Mountain was the solution for the 100,000-year. But that's gone, so we have to think about all alternatives. I'm not an expert in nuclear, but I have some good colleagues who are, and they think a lot about this problem of that exact problem. The other problem I thought you were going to mention is the non-proliferation problem, which is clearly also very important. So that's why I think on a military base, it's a perfect place to put a reactor, because it's probably pretty safe. But it's a good question. It has to be resolved.
At the end, you talked about the importance of national policies, but the only policy you talked about is better regulation. We know that the most important policy would actually be to price energy correctly, and also by time of use and things like that. Can you talk a little bit about how science can work more effectively with policymakers to solve the incentivization
you have
problem?
all night to do this? So this is carbon tax, right? The fundamental incentive I did talk about incentives, would be a carbon tax. And ironically, so many people think it's not an unreasonable thing. If you talk to energy companies, they want to get it over with, and they want to have a carbon tax. They'll pass it on to us anyway, but they want to have a carbon tax. I talked to my friend who does solar. He says, of course, let's have a carbon tax. So I totally agree with you. So how can we be better? This is a much bigger question about how scientists can be better about communicating a lot of these things. A lot of this change that you see that's going on, we have the same thing in vaccinations. I mean, it's going on in many different areas where we've got this loss of confidence in truth or perceived truth. I'm not sure which, but it's a huge question. So there have been a bunch of efforts recently. Carnegie's participated a little bit, but the AAAS, which is just down the road, had a really interesting set of workshops that I actually, when I was back in Chicago, ran one of them on this question is, how do you communicate to people in a way? So here, one thing I hope is I communicated to you guys today in a way you can understand. I'm trying to, I talked a little physics. I had to talk about chemistry, physics, but scientists don't tend to do this well. And my friends in the audience from Carnegie, I'm sure you're all great at this, but many scientists aren't. So I think the first and foremost is some of us like to do it. Those that like to do it should do it. There have been historically people very good at it. I think Maxine was very good at it. There's a guy, so you look at Chuck Vest was another guy who's president of MIT who was fantastic, and he was really here all the time communicating. We just don't have many scientists who are out there telling the story in a way which is, compelling and not just, you got to do the science, fund me to do my science, which is what most scientists would say. And so it's a great question, and like I said, I could spend all night on this one. For all the things we talked about today, it's very important, but it's not just scientists, right? Because you got to have economists. People care about economy. You got to have health people. People care about their health, right? I tried to do a little of that, right? People care. If I told you that in China, because they used to have this thing called the Y River policy, one more point. It was an interesting policy, maybe even a little crazy, but the Y River runs right through the middle of China. And the policy was north of China, north of that, in those days, and still to a large extent, houses were heated with coal, chunks of coal, like the old days in the United States. And so the policy was, if you live north of the Y River, you get coal. If you live south, you don't. I mean, literally, the river's not that wide, a couple hundred meters. It was just a policy, and they decided to do it. So an economist friend of mine did a study and looked at life expectancy north and south of the Y River, and he found a difference, right? When people had to use coal north, their life expectancy is actually significant. It was a couple years, right? It's a tough study. All these economists have tough studies, but it's a tough study. But his study actually showed there was a difference. That can affect people. When you start talking to people about life expectancy and not just about, people, if you live in Beijing or you live in Delhi, you understand what it means to have to live outside. I mean, Beijing, citizens of Beijing are very unhappy, and the government realizes that. But when you talk about health, so getting back to your question, you need health people. You don't just need physicists and chemists to talk about nuclear power. You need all of these people together, and we still struggle to get that group together. We still struggle. So we've got to find the right forums to do that, I think.
Okay, that's a great place to stop. And let's thank Eric again for a wonderful talk.